mirrors in steps that are so small they're just a fraction of a human hair. In fact, the smallest step that we can move is about 1/20,000th of a human hair, and that is so that we can move the mirrors into position so that all 18 mirrors together will be aligned to less than a wavelength of light if you were to kind of go across the whole surface. And so we needed an actuator that could move in these tiny steps, but do it at minus 400 degrees Fahrenheit. And that's a lot of complexity and challenges. And then at the same time, these actuators have to survive launch, and so they have to be able to deal with vibrations, large vibrations, and get the mirrors into the right position initially. Because when we launch the mirrors, we actually have them in a special position that is designed for launching them, where the mirrors are up against, we call it a hard stop, so they're in a nice, secure position. But actually, in the coming week, we're going to deploy the mirrors about a half-inch forward, each of the 18 mirrors, to this point where we can start aligning them. So these motors had to be able to get you forward by about a half an inch and then move in these very small steps. And so there's a lot of different challenges. It took a huge team of people across the country. There's companies that develop the motors in Florida, a company that developed the bearings in New Hampshire. I mean, all over, while Webb is an international collaboration, the telescope itself was actually built within the United States, but maybe 20 or 30 states made major contributions just to the primary mirror itself. That's how significant an effort it was, and that's how much coordination it took. The team from Northrop Grumman, the team from Ball Aerospace, the teams from L3 Harris and ATK that all worked on this primary mirror, they had to work with all these subcontractors from all over the United States to make all these pieces work together.
In fact, I actually believe we have a map that we can show the different collaborators, all over the United States on the primary mirror. I think they're gonna run that. Yes, here we are.
Okay. Yeah. I mean, it's literally all over the country, and obviously the people who kind of worked on this got a lot of frequent flyer mileage. But yeah, I mean, it was a team effort, and we had 3 different NASA centers early in the program working on this. I come from Goddard, which was the lead for the observatory and the telescope, and where it was all integrated. But we had the folks from Marshall Space Flight Center who had a lot of, who helped us with the testing and the mirror technology. We had JPL involved in the algorithms. And then there was this large contractor team led by Northrop Grumman, but with companies all over the country. And for the mirrors, it really was Ball Aerospace that was the lead. So it really took a large collaborative effort. And one of the really neat things about it was when you work on something like the James Webb Space Telescope that is so incredible in its capabilities, it's not hard to get people to want to work on it. You get the most incredible people, and they're so dedicated because they know how exciting it is. And so, and they all, everyone worked really collaboratively. I know a lot of the folks who worked on this, from the people who were, ground the mirrors, the people who put the motors together. I know they're all following. A lot of them send us messages. A lot of them haven't even been on the program for over 10 years, but they're following every little step in detail with a lot of pride. And I will tell you that you see a few folks on television that you're watching in the Mission Operations Center, but for every one of those people, there's probably, hundreds of people who led up to that point who are all watching with pride. And that's what it took to get to this point.
Yeah, it's amazing. I mean, you talk about every step of the way. I remember at one point they were flying parts of the primary mirror for testing on the C-5, which is a gigantic aircraft that has this huge hollow interior that you can take very, very large objects. And I got a chance to talk to the flight crew, and these young men who were actually in charge of flying the airplane were so excited to be flying the James Webb Space Telescope. They just thought that was a wonderful thing to do. So we talked a bit about about building and testing the primary mirrors, and then the idea that these segments, like you said, that they have to function in zero gravity, which is something that you can't do on Earth. You need to make sure you compensate for that, and also at the low temperature. But what comes next in commissioning is something pretty incredible, and that is getting all of these 18 segments to work together. And maybe you can step us through a little bit about what comes next, with a little bit of a timeline and what we're going to do to actually make this thing into one big mirror.
Yeah, well, so first of all, in just a few days, we're going to start exercising all the little motors. There's actually 132, we call them actuators, total on the telescope. There's 7 on each of the primary mirror segments, and there's 6 on the secondary mirror. And so the first thing we're going to do is what we call mirror deployment. That's about a week and a half to 2 week operation. So that'll be starting actually as early as this Tuesday. And that's just to get the mirrors at a point where we can start tipping and tilting them in order to align them. But after that, we'll wait a little bit. We wait about a week or a little over a week for the instruments to get cold enough so that we can get images. So we can't actually we can't get first light until the instruments are cold enough. This is one of the things about being an infrared observatory is you need very cold detectors. So we got to wait for the instruments to get cold. But once that happens, the very first thing we're going to do is we'll look at a bright star, a bright isolated star, and we expect to see 18 separate images of that star that are really blurry. Okay, and it's not going to look real pretty. And
actually, we had an animation. I bet we could run that animation again.
Okay, yeah, let's show that.
Yeah, that's right.
Yeah. So you can see light will come into the 18 mirrors, and they'll behave like 18 separate telescopes because they're not aligned yet. So each mirror actually forms a telescope between the primary mirror segment and the secondary mirror, and that makes a series of spots. And one of the first things we're going to do is find all 18 segments with those spots. And then ultimately what we need to do is get those spots on top of each other. So we'll align the spots, we'll align those primary mirror segments well enough that we have nice spots that we can form on top of each other. We call that the forming on top of each other image stacking. But it is a little bit of a long process because we have to take images, we have to figure out how to move the mirrors. We actually have a special wavefront room here at Space Telescope Science Institute. And we'll have a team of real experts from Ball Aerospace and from Space Telescope Science Institute and from Goddard that all will work together, and they'll get the images, they'll analyze them using software that they've rehearsed all of this with. They've done simulations of all this, and we've tested a lot of this with a testbed telescope that was built up. And they will go through and they'll get those 18 images on top of each other. And at that point, we're ready to get into what we call phasing. And phasing is a little bit like if you think of sort of if you think of waves in an ocean, imagine you have different surfers and they're each surfing on a different wave. What we need is for all of those surfers to be on the same wave. And so we need all of those mirrors to be essentially on the same wave of light. Light travels in electromagnetic waves, and we need them all to be on the same wave of light. Otherwise, we will get images that are kind of confusing. And so we'll go through a process. First, we go through a process called coarse phasing, where we'll get all the waves, all the mirrors lined up to maybe 1 or 2 waves. So imagine the surfers are almost all on the same wave, but not quite. And then we'll go through fine phasing. And fine phasing is the very final sequence. We actually use special algorithms that were developed primarily, actually, if you go all the way back to when Hubble Space Telescope had its blurry problem, the spherical aberration problem. There were algorithms that were developed to figure out the prescription of Hubble so that we could repair Hubble. And those same algorithms are actually being applied here to align the primary mirror in this very final stage. It's almost like you have a blurry primary mirror. And so we'll take images in the main science camera, the near infrared camera, but we'll take them through focus. We'll take different, it's almost like you move the focus on your camera. So we'll take a series of images and then we'll run them through these special algorithms that we've developed. We started with what we did on Hubble, and we've adapted them for the fact that this is a segmented telescope, but that's what's going to allow us to align this mirror perfectly. And eventually we're going to get an image of a single star. So a star will come in very early on, and maybe, a couple weeks, 3 weeks or so, it'll look like 18 separate images. But we think by sometime in March, we'll actually have a star form a single image. And that's kind of the first goal of the alignment process. And then from there, really what we're doing is we're aligning the secondary mirror to give us an image of a star that works in all the 4 instruments, over the full field. That takes about another month and a month and a half. So the whole process is about 3.5 months. We call it wavefront sensing and control. But really what it is it's aligning all these mirrors to act like a perfect telescope. And at the end of all that, we'll be able to hand off the telescope to the science instrument teams who will be finishing up their calibration, and then get on with some of the early science.
Well, that's absolutely incredible, and that's probably a nice place for us to break because we're going to bring on one of those scientists that is waiting to use Webb. So again, talking to Lee Feinberg, one of the senior engineers on the James Webb Space Telescope. Such a pleasure to have you here, Lee. Congratulations,
Thank you, Michelle.
and I
Thank
hope
you.
the rest of the day goes very well for you.
Yep. Thank you very much.
So for those of you that are joining us, you're watching live coverage of the commissioning of the James Webb Space Telescope. We are all here at the Space Telescope Science Institute in Baltimore, Maryland. And I'm Michelle Thaler. I'm from Goddard Space Flight Center. And if you'd like to join us later on, we'll probably have some time for social media questions. So you can use the hashtag #UnfoldTheUniverse. So once again, hashtag #UnfoldTheUniverse. And that will allow us to see your questions and answer some of them on air. So the next person that I'm going to talk to is Dr. Antonella Nota. And Antonella works here at the Space Telescope Science Institute. She's the representative for the European Space Agency. So Antonella, first off, many congratulations. It's been a wonderful morning so far. How are you doing?
It is amazing. It has been an amazing morning. And the team made it look so easy. We know how many years of preparation there were behind the moves this morning, but it just looks so amazingly easy. I'm so delighted to represent the European Space Agency at this time. And this is the moment we have been waiting for so long. So we are ready to move to the next step.
It's incredible. So for those of you that may have just joined us today, we deployed the second and final wing for the primary mirror. And that was a major commissioning exercise. There are definitely things to come, but this is, what's been accomplished is absolutely historic and really incredible. You're looking at live coverage from the MOC, Mission Operations Center.
That command line, and that looks good.
And occasionally you'll hear me pause because we're listening to the commands, so that's all fine. And in between commands, we'll have a chance to talk to Antonella. So, Antonella, you are an astrophysicist, an astronomer, and tell us a bit about some of the major science goals that you're looking forward to. But maybe before we do that, we should back up a little bit and talk about infrared. Why is Webb an infrared telescope, and why is that so important?
It is infrared because it's the sources that Webb wants to look at emit in the air. For example, when we look at the distant universe, we're all familiar with the Hubble Deep Field that Hubble took several years ago. And we know those distant galaxies, born 400 million years after the Big Bang, just at the very beginning. Hubble, with the 2.4 meter, could push us to see that horizon. Webb will go way past and look at the first few million years and see those galaxies that are small, irregular, compact. We want to know how those galaxies became the Milky Way of today. And those galaxies emit in the infrared. Here you see a beautiful fly through the Hubble Deep Field, and it's amazing that in the size of a pencil, we could see thousands and thousands of galaxies, including some very, very old, as I said, as old as 400 million years after the Big Bang. So we're talking 13.2 billion years old. And those galaxies look very different from today. And so I think the challenge for the astronomers is to understand how they evolved from how we look at them then and how we see them today. And Webb will do that. Webb will also be able to actually individually take spectra of these galaxies, because it has powerful spectrograph on board, including, for example, NIRSPEC, the workhorse spectrograph provided by the European Space Agency. And NIRSPEC will be able to actually take spectra. And for all of you who are watching, spectra are when the light of an astronomical target gets split into its component. Like, for example, rain droplets do after a thunderstorm, and you see a rainbow. So why spectra are important? Because spectra tell astronomers what the object is made of. Images tell us how objects look like, but we really want to know the physical, chemical composition, the elements that are there. And for that, we need spectra. And because Webb will be so powerful, 100 times more powerful than Webb, we do believe that we'll be able to take spectra of all these faint objects that we see at the edge of our observable
And
universe.
we are ready to continue with the repeat.
It's absolutely incredible. For those of you that might not be familiar with the Hubble Deep Field, which was the image that we had started with there, when Antonella says the size of a pencil, it's looking down the narrow part of a pencil, that tiny little bit of the sky. Anywhere you look in the sky, there are many thousands of galaxies very, very far away from us. So again, and for our viewers, we often get a lot of questions about how is it that we're able to look back in time. A lot of people, I've actually gotten questions on social media recently about what direction do you need to look to see that far back in time. Maybe you could give us just a little bit of an astronomy lesson about how is it that we can view the early universe?
Yes, you look anywhere, because wherever you look, your eyesight basically looks as far as you can go. And the farthest you go, the farthest you go back in time. So as I was saying, these very faint galaxies that we see in the Hubble Deep Field have traveled for the light for those galaxies has traveled for 13.2 billion years. So we see them today as they were 13 billion years ago. And this is the powerful of this amazing telescope. We can actually look at the beginning of the formation of the universe, because one of the things that Webb will do, it will be focusing on origins. What is the origin of our universe, as well as other origin things like how stars form, what's the origin of stars. So you can see the Webb is going to look, we hope, up to the first 100 or 200 million years after the Big Bang. If we're really lucky, we might even see the first star. Thomas was talking about first star earlier on. That's a challenge. But this is one maybe of the surprises that the Webb will bring us, together with many others, I'm sure.
I've also gotten questions about who gets to use Webb. How is it? One of the questions that I actually got on social media is, do only people from NASA get to use Webb? And that's very much not the case. You work at the Space Telescope Science Institute, where a lot of this happens. Give us a sense. How is time on Webb allocated?
Absolutely. So the entire worldwide community can use Webb to observe. They just need to have a good idea and a laptop and an internet connection, and they can submit their proposal. And their proposal, they will say, I want to use these instruments to make this amazing discovery, will be evaluated by a group of peers, experts in the various fields. And if that idea is compelling, that idea will be scheduled on the telescope. And as we speak, we have already a first year already scheduled of observations that have been given out to the community, to the instrument builders who have the right to get the fruit of their hard work over so many years, and the early release scientists who are actually...
And OC, Dep leads ready to begin with the 3-door latch to 200, move 9 of 20. And
there is a group of
scientists to execute.
Right on that, you have to go to execute.
And you're going to continue.
Hope you go to continue.
This is so exciting to hear this and to hear, what's going on in the MOC at the same time, which is one floor below. And kudos to the team for doing such an amazing work. For astronomers, this is the biggest gift that we can get. And we're just looking forward to see what will bring us. But I was saying the early release science, this is something that the director of STSCI used some of his precious directory discretionary hours to actually tell the community, submit proposals for approximately a couple of hundred hours. And they will be evaluated with this caveat. They will be done right away. The observation will become public. They will go in the archive. They will be made available to all, because this observation will show the capability of this very powerful observatory. So there are a number of programs, some of which Europeans, that are going to execute in the very, very first few months. And those are the ones that will show the world how actually Webb performs. Before that, we will have the early release observations. And those are really the ones that I'm waiting for to see. This is super secret list of targets. I don't know, what targets will be. But I know one thing, that they will be absolutely spectacular. And they will be shown to the world 200 days after launch, at the end of the instrument commissioning. But I hold your breath, because they will be just phenomenal.
I've been looking at the research.
So we've talked a bit about the early universe, and I know that another, primary science goal of Webb has to do with exoplanets. And we mentioned that a little bit with Thomas, but I think maybe you could take us a bit more through how does Webb actually analyze the atmospheres of planets around other stars?
Absolutely. So this is a technique that Hubble had already pioneered, and I want just to tell the community who is listening. When Hubble was launched, we didn't know exoplanets. Now we know that every star has exoplanet around. So this technique allows to study the atmosphere of the exoplanet as they move in front of their host stars, and by doing that, we can see via spectroscopy what actually the components of that atmosphere. And so you can see here the planet basically moving in front of the star, the light dipped, and in the infrared we can see important component elements that are the building block, we believe, of life in the future. So water vapor, carbon dioxide, oxygen, all the complex molecules based on oxygen. Why we're looking for these molecules? Because the ultimate goal is to see if there is life out there. So we start looking at the building blocks. And Hubble has already moved the field forward, but it's a small telescope. We do believe that being 100 times more sensitive, Webb will just revolutionize this field. So our knowledge of exoplanet composition will be just spectacular. And maybe we will find another Earth out there. That's the big, award for this work.
Stand by for review.
Well, absolutely wonderful. Antonella, thank you so much for joining us. I hope the day continues to be joyful and exciting, and after this we all get a bit of a break. So thank you again for joining us. That's Dr. Antonella Nota, the European Space Agency representative here at the Space Telescope Science Institute. Thank you so much.
Thank you, Michelle. Good luck to all.
Thank you.
I see those parameters are good. You're going to continue with the motor move.
So the next person we're going to be talking to is Joe Spofera, and he will tell us a little bit more about some of the engineering aspects of the Webb telescope. For those of you that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. I'm here at the Space Telescope Science Institute in Baltimore, Maryland. I'm Michelle Thaler. And Joe, thank you so much for joining us today. So to begin with, please introduce yourself and tell us a bit about your role on the Webb telescope.
So you mentioned my name's Joe Spofera. So been working on the Webb telescope for 16 and a half years now with Northrop Grumman. Currently the program dynamics lead for Northrop, as well as doing a lot of lead responsibilities for deployments with the team that we have, both what we've done on the ground and what we're doing today here at the Mach for On Orbit.
And how's the morning gone for you? Are you as excited as everybody else and happy that things have gone well?
Yeah, it's been going fantastic. It really has for the last 2 weeks as well. Kind of everything we could have hoped for with all of the operations have really gone quite nominal and quite to our expectations. So it's been a great commissioning so far.
So I guess one of the things that we have that we can show our audience are some footage from the tests that came before the launch of the James Webb Space Telescope, different tests in the clean room. So I believe we're going to roll some video, and you can tell me what we're seeing here, please, Joe?
Yeah, so this is actually the wing we're deploying today. So that was the ground deployment test for that wing the last time through. And actually, if we end up deploying both when deployed, this was our pre-observatory environment deployment. It was the last time that both wings were deployed at the same time on the ground. So you can kind of see the operations that went through there with all of the individuals in the high bay performing their jobs, getting through. So down on the left there, watching that wing deployment, that's Paul Reynolds, who's downstairs right now. as the depth lead doing the deployment, kind of watching for what's going on, both like he would have on the floor there, doing observing the deployment, looking to see any interaction, seeing what's happening. And he's down there right now today with the rest of the mock team, doing that deployment, watching for the telemetry to make sure we see what we want to see during the operation.
And actually, in this footage, you can see that there's sort of this black border on the outside of the mirror, and that's for a very specific purpose. Maybe you could tell us a bit about that.
If you're speaking about the black border on the very outsides of all the mirrors, yes,
that's right. Yeah,
that's there for the frill section that goes around the outside, the fixed frill outside of the mirrors themselves for thermal purposes, so that you kind of have this deep black right next to the mirrors that would not pick up the reflections that the mirrors actually.
Roger.
and then of course that beautiful gold coating, and that's something that we get a lot of questions about as to why the mirrors are coated with gold. You could give us an explanation for that, please?
I'm probably not the best person to give you the explanation for that one, but that is the best material that was determined by a number of scientists and engineers to give us the best performance for the optics and for taking data.
When you see the deployment and the tests that were done, the thing that amazes me is that all of this was done here on Earth. There was no way to take this up into space and test it in space. And of course, in space, you don't have the influence of gravity, whereas here on Earth you do. How do you design a test that you know that it's going to work in zero gravity? How do you design to take that into account when you're testing here on Earth?
Right, so the key thing there is we have to have a very good understanding of the loads that we want to see in the deployment and the loads that we want to kind of counteract or counterbalance in the gravity field. So we do want to try to maintain the resistances that we're trying to characterize or understand. So there are certain harnessing or insulation that provides a drag or resistance to the deployment. We still want to capture that in the test so we can characterize it and understand it on the ground. But you do need to counteract the gravity. You need to take away the fact that there's weight reacting on hinges and different locations in the deployable hardware. So there is an offload system that we use for that, and it was visible a little bit in the video that you did show, and I don't know if we'll be going back to that or not, but in the case of the wings, there was an overhead system, and actually you can see it right here. So there's a cable going up from the wing itself, from some hardware attached on the back so that we can attach basically through the CG of the wing. And you can see the cable running up to the crane structure to what looks sort of like a balance beam or a teeter-totter that's up there. And that cable, the beam that's up there can pivot and rotate, and the rotation point's aligned to the rotation axis of the wing so that you get a one-to-one rotation there. As the wing is turning, it's turning the hardware up above in the crane area. And at the opposite end of that rotating arm is also a weight to kind of balance that out. So you get a load or a tension in that cable that's effectively equivalent to what the wing weighs. So that now as you're rotating, the hinges that you have in this system don't actually see the weight of the wing. They're nearly weightless, as best as we can on the ground, so that you can instead try to capture just the loads of the nominal flight deployment, which would be, like I mentioned, something like a harness or some insulation, or some very low nominal drag that you get from driving at the one hinge as you rotate.
Absolutely wonderful. So it's been such a pleasure having you here, Joe. Congratulations again on everything that's happened this morning and the continued commissioning of the telescope that's coming up. So we'll let you go. Thank you so much for taking us through some of this testing.
Thank you very much.
Good to have you here. So for those people in the audience that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. Today we have successfully deployed the second wing of the primary mirror. We now have the whole primary mirror together, and we are currently involved in latching that into its final place. So that procedure will be happening for a couple more hours, and we'll be here to the end of it. Right now, however, we will probably take a short break in our commentary, and when we come back, we will talk to some more experts on the James Webb Space Telescope. You'll be seeing more live coverage from the MOC, the Mission Operations Center, here at the Space Telescope Science Institute in Baltimore, Maryland. And I'll be here to take more of your questions on social media. Once again, you can use the hashtag #UnfoldTheUniverse, and we'll get to some questions after the break. So thank you very much, and we'll see you soon.
I pulled up the YouTube stream at the TV Live.
The motor moves in progress. And the motor moves complete.
Copy.
Okay, and OC, Depleted has confirmed that those latches look good. We're ready to continue with the 3-door latch to full. And that's move 13 of 20.
For complete.
Yep.
Yeah, we're
Stand
ready.
by.
Standing by.
You could just steal one off one of the other wireless, like the Alpha PSC station. That's what I usually do. It's all the same batteries. Yeah, we gotta take advantage. We don't want to sit still.
Hello, Julie.
Hello.
So,
We're currently in our final steps of the first latching of the 3 degree of freedom latch. This is the bringing it up to its full load. They've been, as you've been talking with your other guests, you can hear that they've been talking through all the steps as they move through all the different levels of load on the latches, and they're coming up on what they call the 3-door latch, and it's going to be loaded up to its final and complete step. As they've been going through, they've been checking out their system, checking out their motors, making sure that each step of the way that everything's good. They're in their final checkouts now, and this first complete latch is a big milestone.
excellent. For those of you who've just joined us, that's Julie Van Kampen. She is the Deputy Commissioning Engineer for the James Webb Space Telescope, and I am Michelle Fowler. We're joining you from the Space Telescope Science Institute today in Baltimore, Maryland. And earlier in the day, we successfully deployed the final wing of the primary mirror. And what's going to be happening for the next couple of hours is latching that into place. Now, during our broadcast, you'll probably see us pause as we listen to commentary from the MOC, or the Mission Operations Center here. So if we're pausing mid-conversation, we will start right back up as soon as we get the call. And of course, we're operating under some very interesting circumstances today because of the COVID surge. We were all isolated. I'm downstairs in a conference room, so I can speak to you without a mask on, and Julie is in a room upstairs. So we're all isolated from each other to keep each other safe. You'll notice that everybody is masked inside the control room. We had a large and beautiful set at Goddard Space Flight Center that we were going to do perhaps a much more polished and professional looking broadcast. But in a way, this is kind of wonderful because it was so important for us to bring you all along on this very historic day. This is the largest and most complex space observatory ever built. It's built to answer some incredible questions about the origins of stars and galaxies and planets, the origins of us, the possibility of there being environments like the Earth on planets around other stars, and many, many things in between. So the rocket was launched carrying the James Webb Space Telescope on December 25th from French Guiana, from Kourou, that's in South America. It's now traveled more than 600,000 miles on its way out to its final resting place at L2. L2 is a Lagrange point, which is a balance point between the gravity of the Earth and the Sun. That's a wonderful, stable place to put an observatory. Webb is on its way out there right now. But as it does so, it is unfolding. The observatory is so large, it had to be folded up to fit inside the rocket. And that's a unique thing about Webb that has not been attempted before, this degree of unfolding and commissioning. And that's why we wanted to bring this to you live. Because this is a live broadcast based on an actual engineering event, the schedule is not known to the minute. The engineers will call out the commands, as they see fit and at the pace that they want to go at. So this is a broadcast that is not only live, but sort of, very much spur of the moment as we wait to see which commands come in and how long they decide to take from each step. But Julie, I think you can reiterate to everybody that things are going very well this morning so far, aren't they?
Yes. So far, our actual motion of the mirrors segments as they folded from being back alongside of the structure to its final position as you see it now in our visualization tool went extremely well. The motors work perfectly. The launch releases before that went perfectly. And now they're in the process of latching into their final position so that those mirrors are aligned and ready for the next steps, which Lee had spoke to just a few minutes ago.
So I'm just looking at some of the social media questions that are coming in, and there's a lot of different ones on the mirrors. Actually, this is probably one that we can answer. So it's Jemison on Twitter states, my 8-year-old son wants to know why the mirror is a set of hexagons. Why was that shape chosen for the mirror? Julie, you can probably answer that one.
Sure. As you can kind of see in the picture, the hexagon shape packs in nicely into a circle. Most telescopes you can buy in the store or anywhere that you've seen typically in movies or whatnot is has a round mirror. It gives you the best amount of light collected per use. It gives you a nice usable beam. The hexagon approximated that very closely. It has a nice packing shape. You can see how it fits in around the optics that kind of poke out. That nose in the middle is called the Aft Optics. It's the optics that kind of fold the beam a couple times before it sends it back into the science instruments. The outside shape of the mirror itself, it doesn't matter as much. Each of the edges of those mirrors are very carefully handled to make sure that they don't have glints off the edges, and to make sure that the edges are perfectly handled with how the gold coating reaches the edges of those. So the hexagon gave us a great shape for handling the mirror in its movement, the way that Lee had described, and it gave us the best approximation of round.
Okay. And it's worth mentioning, we've got a couple different questions about the gold coating. So we're just going to pause, see what they're saying in the mock.
Go ahead. This is Ocean.
So at this time, I can really confirm that depth lead is ready to begin the 3-door cup latch to full. And that's going to be motor move 13 of 20.
Copy that.
And that command line looks good. You're good to execute.
Copy. To see you have the go to execute.
Executing.
And you're good to continue.
Copy, go to continue.
Roger.
Nice to see you smile there, Julie.
Yes, so our first
when you think about the operating
position.
Oh, no, not at all. As you say, we're actually right now in the latching procedure. This will take a couple of hours as the mirror was moved this morning, and now it's being latched into its final place. There are a couple different questions on how we design things to operate at this, very, very low temperature. In fact, this may be something that you as a mechanical engineer. So Jerry from Twitter asked, what kind of lubricants are required for the bearings of a wing segment and mirrors, or are they electrically heated in the way that they can actually, move around at these very low temperatures? Like you said, not much more than 100 degrees above absolute zero. Can you give us a sense about how you design an actuator to actually move and function? Things to actually swing around when they're that cold.
That's a great question. And it's been one of our major challenges. As you heard a little bit
Yeah,
about
I
Lee
see those
talking,
parameters look good, so we're going to
and different
continue with the motor move.
times along
Copy
our
that.
uh,
Go to continue.
Roger.
that the I'm sorry, I lost my train of thought. That thinking about what they
There's
were
a lot
just saying
going
on the
on.
left. But when Lee was talking about the mirrors swinging into position, they have a particular type of lube on it. We did heat these particular ones up because they are what is called a wet lube, which means that we want them to be at a special temperature. Many of our other actuators, the ones that Lee was talking about, that on the backs of the mirrors and lots of other
And the motor
places
move's
throughout the
in
telescope,
progress.
call what is a dry lube. And most of the time, the dry lube that's used is a molybdenum disulfide, and it's this. It's essentially a very soft material that is not a liquid at all. It's actually a solid material that gets coated onto the surface of a joint, and the surface of the joint kind of smears across that soft metal and has a very low friction. It's interesting because we're using it at such low temperatures, and as we've talked about before, there was such a long period of time in designing and building Webb. So one of the major things that we had to go through was a lifetime test. And in our lifetime test, it's very difficult to simulate exactly how long you're going to be in test in the ground. So if you want to say that your mechanism is going to be good, from the day we coat our joint to the day that we're finished using it on orbit, and maybe that's a period of 10 years, maybe that's a period of 20 years, maybe we get lots of fuel and we get to do it for 30 years. How do you get to qualify that?
Station to launch, getting LOS and transition to matrix in an hour and 10 minutes.
So the operations on orbit, in a way, might be actually the simplest part of it. It's steady state. It's always steady state temperature. It's always a cryogenic temperature. It doesn't come back to air. It's never exposed to oxygen again. Oxygen is one of the things that can degrade surfaces. It oxidizes, creates little chunky pieces of oxidation. So once we're in orbit, we're pretty good with this. But the qualification had to figure out, well, how many times are we going to move this mechanism in air? How many times we're going to use it in vacuum? How many times we're going to use it at cryogenic temperatures? All through our testing lifetime. And then put on top of that, how long is it going to be used in space in those conditions? And will it have enough life of that joint? So that was a great question.
Yeah, absolutely. I mean, this is part of this idea of cryoengineering, making things that are going to work and work for a long time and work reliably under these sorts of temperatures. And actually, there are more questions coming in from social media about, for example, Dorian on Twitch said, "How did you manage to test the focusing of the mirrors on Earth with all the deformations?" So we've mentioned that it's not just one of the deformations is caused by gravity versus no gravity, but there's also the deformations caused by temperature. And this is something that I've had the pleasure of being able to watch for the last years, is all of the different stages of testing of this. Maybe you can talk a bit about some of the cryo tests of this that this telescope had to go through.
Sure. The way NASA approaches this, and all the contractors that work for us, and ESA too, in their nominal test program, is you start at the very most basic level. You saw some of the pictures of the mirrors being built and assembled, and Lee talked a little bit about their manufacture along the way. Well, that happens with every component. Is you start at the component level, the piece parts, and you start at testing them and understanding them. And even at cryogenic temperatures, you might start off with just doing cryocycles to make sure that those.
Stand by.
Standing by.
So
hear us pause in the conversation as we listen to the box.
And
So yes.
yeah,
Sometimes
sometimes I get more conversation in my
I
ear.
can confirm that Dep Lead is happy with the 2-door latch to full. We're ready to continue with the 3-door. Oh, sorry, he was happy with the 3-door latch to full. We're ready to continue with the 2-door latch to full, and that is motor move 14 of 20.
Copy.
And that command line looks good. You are go to execute.
Copy that. CC, go ahead and execute.
Executing.
And you're go to
So
continue.
Copy, go to continue.
just to wrap up our conversation on cryo testing, like some materials, like specifically our carbon tube material that you could see in our current visualization with the tubes that hang the secondary mirror out in front of us, are all of our backplane materials. They're made of a carbon structure that has a cyanate silosane polymer that binds all those carbons together, and that's like a special polymer that's designed for high stability at cryogenic temperatures. But in order to deal with it at
parameter
room
review
temperature and know it at a
Standing
cryo
by.
temperature, you have to go through a cycles to kind of cryo stress relieve it. And the mirrors had the same thing. So there's lots of stuff that we do early on to help these materials deal with that cryogenic temperature.
So Julie, give us just a quick translation of the commands that are coming in now. What are they saying?
Copy, go to continue.
Roger.
So they're in their final stages of moving each of these latches into their full position, so they get their full load on them, and this will be the final thing that holds that mirror down. We did this with the other side yesterday. Once it's in its final position, we never touch these latches again. Every motion from that point forward is happening at the mechanism level that's behind each of the mirrors, and not at the frame and the structure behind it that we're latching into position today.
Well, Julie, thank you so much for joining us. Hopefully, I think we'll have a chance to talk to you a little bit later in the broadcast. For those of you that are just joining us, you're watching the live commissioning of the James Webb Space Telescope.
All stations,
And
this is GSE on ops. Be advised, at this time we have just a little more than an hour before we begin our activities to hand over from DSN Canberra to DSN Madrid. That will start at 18:15, when we will lose coverage on the Madrid backup station, or Canberra backup station, DSS 36. We will have command and telemetry through Canberra Prime, DSS 34, for another 5 minutes. At 18:20, Canberra Prime will bring down their uplink, and we will have single antenna telemetry only at Canberra for another 5 minutes. At 18:25, Canberra will end their track. Madrid Prime, DSS 54, will start their track, then bring up the uplink as soon as they acquire telemetry. And at 18:30, 5 minutes later, our Madrid backup station, DSS 56, will acquire the downlink. So to reiterate, we will lose backup telem at 18:15, lose command at 18:20, get command back at 18:25, and get backup telem back at 18:30. There will be continuous telemetry despite the 5-minute command outage, except for a few interruptions. I will call them out before they occur.
Copies. Thank you, Jesse.
Once again, thank you for joining us, Julie. All right, so we're listening to live commands from the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm Michelle Thaler. For anybody just joining us, you're watching live commissioning of the James Webb Space Telescope.
Be advised, at this time you have 1 hour of command remaining on DSN Canberra.
Copy that.
What you hear them talking about is something called the Deep Space Network, the DSN. The way that Webb communicates with the Earth is that there are several large antennas, radio dishes around the world. And of course, as the Earth turns, different dishes come into view and out of view of the Webb telescope. The Webb telescope itself is now more than twice as far away as the Moon. It's about 600,000 miles away today. and it's going out to about 1 million miles away, a point called L2, the Lagrange point, a balance between the gravity of Earth and the Sun, a wonderful place to park a telescope for the long and hopefully very successful mission ahead of it. It's been an absolutely incredible journey. The James Webb Space Telescope launched on December 25th from French Guiana, from Kourou. This is the main launch site of the European Space Agency, one of the major partners in the James Webb Space Telescope. Other major partners include the Canadian Space Agency and, of course, NASA. And the telescope has been on an incredible journey. I have been honored to be working at Goddard Space Flight Center while much of it was built. So I was able to see some of the testing and some of the building of the primary mirror, as well as the instrument package. And then it was shipped to Northrop Grumman in California, where it was actually put onto the actual spacecraft. And you see here some of the integration. You see that large primary mirror, and that's exactly what happened earlier today, is that the final wing was deployed. So we now have the full complete mirror deployed and is now being latched into place. What you see here is the testing of the incredible sun shield. This is a 5-layer shield made of Kapton, a very light, very strong material. Each one of those layers makes the layer above it a little bit colder until you finally get up to the telescope that has an operating temperature of under 400 degrees, under minus 400 degrees Fahrenheit. So just an incredible marvel. That was Julie Van Kampen, who was talking to us a bit about some of the testing that was required to make sure that different components actually worked at that incredible temperature. So here you see a beautiful picture of that large primary mirror. The mirror segments are each one of those mirror segments is a bit over 1 meter in length. So the mirror itself is about a little bit over 7 meters, about 7.5 meters across, which is absolutely incredible. A long journey to get it here from Goddard Space Flight Center, the different universities where instruments were built, to Northrop Grumman, where it was all put together and finally tested, and then put on a boat through the Panama Canal and to Kourou, and then the European Space Agency's launch site. Picture perfect launch early in the morning, Eastern time, December 25th.
I'll see you standing by.
You'll hear me pausing in the commentary just so we can listen to what the commands are. Currently, they are latching the telescope into its final place, and it's been an amazing couple of days.
To continue with the motor move.
Copy, go to continue.
So,
Roger.
the first thing that happened about a week ago was the deployment of the sun shield. That was very dramatic and incredible. And then came the secondary mirror. The secondary mirror is on a large boom that has to come out in front of the primary mirror. It's the focusing mirror. The light from all of those wonderful gold-coated mirror segments, they're all focused up to the secondary mirror, which then directs the light down into the instrument packages. And you can see here some of the major deployments that Webb has been through. The very first deployment, which we actually saw on cameras from the rocket, was the solar panels to power up the spacecraft. And here you see that incredible sun shield being unfolded. So there are the front and back components of the sun shield. Webb was then lifted away from the sun shield, where it will be isolated in cold operating temperatures, like I said, near minus 400 degrees Fahrenheit. And that was a baffle that was put up to help steady itself in the solar wind, a wind of particles from the sun. And now we're going to see the deployment of the sun shield. This, of course, is a computer animation. We did not have any cameras on Webb itself. But one of the things that we've been able to do today is see live visualizations from data from telemetry that's been coming down from the telescopes. So the telescope has been sending us signals as to what configuration it's in. And we've been following that this morning. And of course, that was one. Here you see that secondary mirror coming out on those long booms. And then yesterday, you'll see the next thing that happens is one of these mirror segments was clicked into place. That was the activity yesterday. And then this morning, the final wing of the primary mirror is in place. So we have a very special guest joining us next. We have Greg Robinson. And there are a few different people, including Thomas Zurbuchen, who had mentioned Greg earlier in the broadcast today as being one of the just most incredible leaders.
I can see that
amazing team working together.
Depth lead has confirmed that the latch-off stow performed as expected. He's ready to continue to the top one door latch to safe, which is 16 of 20.
Okay, copy. Stand by one, please.
Standing by.
And Greg will continue with you as soon as we hear the end of that
Open
commentary
mic
from the
on
mock. I think we're good to go. Welcome, Greg.
Thank you, Michelle. Glad to be here.
Oh, what wonderful to have you here. Congratulations on this very successful and exciting morning. How are you feeling right now?
I'm feeling pretty good. This is certainly a huge milestone to complete all of the deployments. As you know, this was the stage where we thought we had the most risk in the mission. Still have a long ways to go, but certainly it's great to have this part behind us, at least in.
So tell us a bit about your role on the James Webb Space Telescope. I know now you are at NASA headquarters, and what has been your role for the larger mission?
So I've been on the program 4 years, so I'm the baby. My role as program director is to provide oversight to the project, execution, leadership going up to the administrator level, to what we call the non-floor, and external with our stakeholders, plus our international partners.
And people, time and time again, have commented on what a wonderful team this is. Can you give us some observations and maybe some personal stories about just how well this team has worked together under some very challenging circumstances?
Standing by. Stand by.
Standing by.
Yeah, this is certainly an amazing team. It's quite large.
We've reviewed those parameters and they look good. We are good to continue with the motor move.
Copy, go to continue.
Roger.
I'd love to hear the voices because that means we're making great progress. So I'll stop in the time. Yeah, so a very large team across the globe. I think you've mentioned that. And certainly a lot of really good leaders at different locations at Goddard, at Northrop, at the Institute here, and across the entire industrial base in the U.S. and across the globe. Really good team, certainly at headquarters at my level and Thomas, the administrator. We've had tremendous support, engagement, and focus. And so, and the two, it's kind of funny going into the mock last week. I talked to many people, no idea which badges they wore, because it's truly one team.
Go ahead.
I think this is often something that surprises people about large missions, that it's not just a single.
This move will take about 14 minutes.
Just as listening to the mock
Repeat
commands.
your last step-ups, please.
Oh, the move will take about 14 minutes.
14 minutes. Copy that. Thank you.
For those of you joining us, we're listening to live commentary from the Mission Operations Center, and they are latching in place the wing of the primary mirror that was deployed earlier today. That process is going to take a few hours, and we will be here through the whole thing. So at the end of it, we'll be able to say that procedure has been completed successfully. But Greg, we were just talking about that. A lot of people don't realize that pretty much all of the large missions that they may have heard of, and everything from Mars rovers to the Hubble Space Telescope and now the Webb Telescope. These are international collaborations, and not just that, collaborations between industrial partners, government partners, university partners, all of that. Maybe you can give us a sense of just the range of partners that went into something like the Webb mission.
So the partnership, certainly internationally, includes the European Space Agency and the Canadian Space Agency. Truly great partners. They partner with us on many missions, and they've brought a lot to the table, instruments and the Ariane 5 launch vehicle. And we really appreciate, of course, in the U.S. States, 14 countries across the globe. So a tremendous amount of support and engagement and actual development to get Webb to this point and further along in the operations. So it's been a huge team. And the industrial base is almost limitless. If I try to name all of the companies and institutes and universities, I'd probably be here until late today. And over the life of the development, more than 10,000 people have actually touched Webb. And externally, we talk a lot when we go to schools and things about technical careers. Many people have touched Webb, made it possible, including public affairs and finance, all types of disciplines. Of course, the heavy lifting was done by technical teams.
And what was your path to Webb? You were mentioning all these different technical careers. So what what was your education, and how did your career bring you to this point?
So I'm a double E, and I started my career in industry, and then many years ago, seems so long ago, at Goddard Space Flight Center. I've had many leadership roles at Goddard, at headquarters. I was deputy out at Glenn Research Center for a couple of years. And prior to this role, I was an SMD for programs, which consists of oversight of all of the SMMs. I think at the time there were between 110 and 114. And then 4 years ago, someone twisted both of my arms and said, let's go get this thing over the goal line. And I think we're pretty close.
Just of course, you know that NASA loves acronyms. SMD stands for the Science Mission Directorate. And as Greg was saying, the Science Mission Directorate now has, it's over 100. Of course, it changes week to week as different missions launch and different missions come to the end of their lifetime. But over 100 missions, all being Science Mission Directorate at NASA. And again, perhaps those of you who don't know what a double E is, Greg, what do you mean by that?
Electrical engineer.
Absolutely.
Sorry.
So this, the wonderful groundwork that you've laid with these partnerships, and working together, I mean, how would this mission shape the future of astrophysics at NASA?
So you've probably heard from some of us, and you heard from more. So from what I would call a layman standpoint, certainly for NASA, it's huge. It adds to the history of what NASA can do. Very complex, large missions that really open the doors for many discoveries. And of course, you've heard all of the discoveries we're certainly searching for with Webb, including looking back 13 and a half plus billion years between there, and looking at habitability of exoplanets, and also studying within our own solar system. So it's going to do a lot better than anything we have today. So certainly to that. But from a programmatic standpoint, it certainly shows within NASA, within the broader community, stakeholders, and across the globe, what NASA is capable of doing. And we can actually do a lot more when we have excellent partnerships like we have today with our two primary partners.
Well, Greg, thank you so much for joining us. Again, congratulations on a wonderful morning, but congratulations on the excellent leadership that you've lended to this program. And we're going to take a short break now. We're going to keep these images up in front of you. There you see Greg and me. And then when we take a break, you'll see continuous images from the MOC, the Mission Operations Center at the Space Telescope Science Institute, and also our Observatory visualization tool, which you see on the left. This is a computer-generated image, but it's based on real-time data coming down from the observatory. So we're going to take a short break, and we'll be back in just a little while to continue our live commentary of the commissioning of the James Webb Space Telescope.
All the stations off and off. Current step 693.085. We still have 3 more minutes to go.
And I see that motor move's complete.
Also copies.
RTCP is complete.
And DevOps copy. And OC, we're ready to continue with 693.086. Top 1 door latch to full, 17 of 20. The command line looks good. You're go to execute.
Copy. You see you have to go to execute.
Executing.
And you're go to continue.
Copy, go to continue.
Roger.
And stand by for parameter review.
Post is standing by.
Okay, and OC, those parameters look good. You're go to continue with the motor move.
Copy, go to continue with the motor move.
Roger.
The motor move is in progress.
Also copies. All the stations are turned off. We have 47 minutes to get LRS and transition to Madrid.
And OC, this is GSE on ops. Be advised, in 32 minutes will be the end of our command coverage at DSN Canberra.
Also copies. Thank you, Jesse.
And I see we're about halfway on this move.
I'll take up.
Gotcha. Cool.
Station 3-4, this is JMOC on JWest Prime Ops. I think I must have a typo in my notes.
No, see that motor move's complete.
Your drive off time for your
Also copies.
Okay, I see this is Aft Ops. The motor move's complete. We're 17 of 20. We're ready to continue with 693.088. Bottom one door lash off stow, 18 of 20.
Copy that. Sunday window.
And that proc looks good. You're go to execute.
Copy. Ceci, you have the go to execute.
And you're go to continue.
Copy, go to continue.
Please stand by for parameter review.
Also copies. Standing by.
And OC, those parameters are good. You're good to continue with the motor move.
Copy, go to continue with the motor move.
Jen, you're coming in very low, be advised. You have the,
I'm going to go to Oxford.
all right. Review about 3 by 5. Tommy. Might want to just turn your mic gain up a little bit.
Hello and welcome back to live coverage of the commissioning of the James Webb Space Telescope. I'm Michelle Thaler. I'm joining you here from the Space Telescope Science Institute. And you are listening to live commentary. You'll notice that I'm pausing because there are different commands coming in from the Mission Operations Center or the MOC. What has happened this morning is we have deployed the final part of the primary mirror, this giant gold-coated mirror of the James Webb Space Telescope. There were 2 wings that had to be deployed into place for the whole primary mirror to be functioning. That has happened, and what is happening now is latching. These are latches that will secure the mirror into its final configuration, and you'll hear commands going on. I'll pause the commentary when I hear different commands coming in from the Mission Operations Center. So it's been an incredible morning, an incredible journey for all of us on the James Webb Space Telescope. The telescope launched
the motor move complete.
And is now on its way out to its final location, its final parking orbit at L2, a Lagrange point, about 1 million miles away from Earth. Of course, coverage is a live event, and this schedule is set by the engineering. So we don't know exactly what time this will end. The idea is that we will be here through the latching.
It looks like that proc's complete, and we are ready to continue with 693.089. Bottom 1 door latch to safe, move 19 of 20. Command line looks good. You're good to execute.
Fire gas. CC, you have to go to execute.
Executing.
And you're good to continue.
Copy, go to continue.
Roger.
So by the end of the broadcast, we will have the final confirmation that everything is latched into place. And this has been an amazing couple days of the major installations required for the functioning of the James Webb Space Telescope. It's not the end. We still have plenty left to do. So the next thing after this is that the telescope will have to cool down, and then we will begin commissioning the primary mirror, which is in 18 separate segments. Each of those segments can be individually moved to focus this into one large functioning telescope. And I believe with me, I'm going to have Julie Van Kampen. Julie is the Deputy Commissioning Engineer for the James Webb Space Telescope. Hello, Julie.
Standing by.
And so what you'll see on your screen is you'll see Julie and I in the bottom here. Above us is live coverage from the MOC. And at the moment it's just us. And then there'll also be data coming in on an observatory visualization tool to show us what the observatory is doing at the moment. So Julie, we have a few moments. And I know that one of the things we're getting lots of questions about are careers in science. And we have 2 sort of different people to represent engineering and the science aspect of working for NASA. So how about you start out? Tell us a bit about careers in science and how you came to be in the position that you're in now, Julie.
Well, going through, everybody that you've talked to today has talked to. You've asked the same question and gone through the how they've become careers in science, and I think it's really interesting to hear how everybody kind of goes back to like how they got started, and then they talk about. Kind of where they went through their career. But I think a couple of people have said a couple of really important things. And you even mentioned it once when you were talking about the pilots that flew the plane to bring the telescope to a particular place, or portions of the telescope to a particular place. What's always been something that I knew that I wanted to do. I didn't necessarily know I wanted to be an engineer, and I didn't necessarily know that I wanted to work for NASA, but what I did know is that I wanted to do something that I really cared about. And I think, as you've gone through your program today, you've seen technicians working in the clean room, You've seen machinists. You've seen people who had to work in coding departments. You've talked to lots of engineers and scientists. And the thing that everyone has in common, and Greg had mentioned how many people over the years had really kind of touched JWST throughout its life, and whether you're a lawyer or you're finance or whether you're in the media department here today, you have to be really excited about what you do. It almost doesn't matter what it is that you do or where you wind up or what path that you take to do there, as long as you find it so compelling that you want to get up today and that's what you want to do. And that's when people say, well, what should I do? What should I study? It almost really doesn't matter in particular what you pick, as long as you are really interested in it and as long as you find your path to be the most exciting thing of your life. You spend so much of your life doing it, you got to enjoy it.
I couldn't agree more, Julie. I mean, there's a few things there that you touched on that I think are really important. One is the range of people that can work for an organization like NASA or our partner organizations, either universities or in the aerospace industry. I don't just work with other scientists, like you mentioned. When you have all of the different nations and all the different companies involved, you have lawyers, you have people that are experts in finances. You have all of the people that are generating the incredible animations that we're seeing, and the computer scientists and the graphics people and the visualizers, the people that can make these beautiful images that we see, the people that will eventually work on the images that come down from Webb. There are so many different ways to work at NASA. And, for me, it really was a dream early on to work at NASA. That's because I couldn't get these questions out of my head about space. I remember we opened the program today with a little bit of a voiceover from Carl Sagan, who was a famous scientist when I was growing up. And when I was 10 years old, he had his program Cosmos. That was back in 1980. And I was so taken with the questions and the drama of the universe that even though by the time I got to college, I didn't necessarily find the physics and math classes easy. I didn't get the best grades, but I could not stop thinking about this. And when people sometimes, parents will say to me, how can I encourage my child to be a scientist? And just like you said, I'm not so concerned about people becoming scientists necessarily or engineers. I'm concerned about them following their own curiosity. And then
Exactly.
Life becomes a joy. Yeah. I mean, I am so privileged to work with people like you and people that we're seeing today in the films and the footage live here at the Space Telescope Science Institute. The amazing thing is the people that we work with and the passion that we share.
I agree with that. Thank you.
Right. So I believe what we're going to do now is talk a bit about the science of Webb. So we just talked about all of the passion and all of the questions that we answer with the Webb telescope. And being an astronomer, like I said, this is a particularly exciting time for me. I am personally very, very much looking forward to the data that the Webb telescope is coming back. So I believe there are a couple different animations we can run while we talk about the science. First of all, let me talk about why the Webb telescope is an infrared telescope. And this is something that's different from our eyes. Our eyes are not sensitive to this color. So infrared is a type of light that is a lower energy light than the light that our eye sees. What you see here is the electromagnetic spectrum. That's a term for all of the type of light that exists. And our eyes are only sensitive to a tiny bit of that. So, the electromagnetic spectrum includes things like gamma rays and X-rays and ultraviolet. That's over to the left of your screen. And those are types of light that are just too high energy for our eyes to detect. And then as you go onto the other parts of the electromagnetic spectrum, you have things like infrared light, which we commonly think of as heat light, or also microwaves and radio. These are all parts of light, but just things that we are not sensitive to. And there have been telescopes before that have looked a little bit in space into these different types of light. The Hubble Space Telescope saw a little bit, and still does see a little bit into the ultraviolet and the infrared. And the Spitzer Space Telescope was a mission that launched that I was part of all the way back in 1998. I started working on the Spitzer Space Telescope mission. And you can see that James Webb was designed to look at this particular wavelength of light, infrared light. And infrared light has several incredible advantages to it. This is a famous image from the Hubble Space Telescope, invisible light, the type of light that our eye sees, of something called the pillars of creation. These are giant clouds of dust and gas. They are hundreds of billions of miles across. And this image that you see here in infrared, that's a real image. So this is an image taken by the Hubble Space Telescope looking a little bit into the infrared. Our eyes can't see this. It's invisible to our eyes. But all of those stars that you're seeing there are really there. The light was obscured by dust. Visible light that our eye sees is very easily obscured by dust. And some of the more interesting things in the universe actually happen inside these big clouds of dust and gas. This is a visualization, again, produced by our amazing animators, based on real Hubble observations of the Orion Nebula. The Orion Nebula is one of the largest places close to us in our galaxy where new stars and planetary systems are forming by the thousands. And inside this cloud, we see all of these young stars, young planetary systems. Normally, much of this cloud is obscured from us. The dust is so thick we can't see it. But in infrared, we can see right through that dust, and we can actually really have a chance to witness the birth of stars and planets themselves. So infrared has this very specific property of being able to see places we can't see with visible light. And this is also something that comes in handy with seeing the very early universe. The farther away you look out into space, the longer that light has taken time to travel to us. Light travels at 186,000 miles per second. That's very fast, but it is a finite speed. The Hubble Space Telescope could see so far away that the light was coming to us about 500 million years after the Big Bang. But Webb can see farther still. Webb can actually look so far away that it's looking back to a time where the light left when the universe was only a couple 100 million years old. That's amazing. That's actually the time when the very first galaxies were forming. And this is a visualization based on physics, based on how we think the early universe came together. What you're seeing here are young galaxies. A galaxy is a family of hundreds of billions of stars. And in the early universe, there were many smaller galaxies that began to combine into the large galaxies we see today, like our own Milky Way galaxy. Our own Milky Way galaxy today has 500 billion stars, more than 500 billion stars. It's 100,000 light years across from end to end. But we're also part of a cluster of galaxies. And galaxies seem to cluster together based on something called dark matter that was present in the early universe. Webb is going to be probing this mysterious form of matter and trying to understand how it led to the formation of galaxies and, of course, the stars, the planets, and everything else that we see today. What you're looking at right now are some beautiful pictures of galaxies from the Hubble telescope. Another thing that we're really proud about with the Webb telescope and really looking forward to is we think we will have the ability to understand what exoplanets are like. So exoplanets are wonderful objects that are planets going around other stars. So far, we can measure the mass of these planets and we can measure their density, but we really have no understanding of their environments. Do they have atmospheres like the Earth? Are there things like water vapor present, carbon monoxide, carbon dioxide? The way we find that is we watch the planet actually, we call transit in front of its star, actually make a tiny little solar eclipse. And when that happens, the starlight shines through the atmosphere of that planet. And some of it goes right on through the atmosphere and continues toward us. And the Webb telescope can pick up that radiation and actually analyze what's inside that atmosphere. The reason we're able to do that is that every different chemical, like, for example, oxygen, carbon dioxide, water vapor, methane, all of these have very specific wavelengths of light that are absorbed. And because of that, with the light, we can tell what that atmosphere is actually made of. So it's a wonderful chance to give you a little bit of a recap of some of the major science goals of the Webb telescope. And I guess at the moment, we are getting ready for some of the more significant calls. We're going to take a small break right now as we get ready for some of the final latching procedures. So here again, I'm joined by Julie Van Kampen. We will be back later. We are going to be taking a short break as we get ready for some of the finale of the latching procedures coming up. You're watching live coverage of the commissioning of the James Webb Space Telescope.
Yeah. They started at 54, and it takes 15 minutes.
parameters up there fast, and I'll do faster review.
I'll try.
These are really easy between 700.
They've been the same the whole time.
Okay, as soon as this proc's complete, I'm gonna pull it up.
Yeah.
All stations be advised, we have 10 minutes of command coverage remaining on DSN Canberra.
OC, that motor move is complete.
Copy, copy.
The parameters results look good.
Okay, OC, that proc completed. We're ready for 693.090, bottom one door latch.
Door latch to full, 20 of 20. The command line looks good. You are go to execute.
And you're go to continue.
Copy, go to continue. Roger.
At the Space Telescope Science Institute in Baltimore, Maryland. And I'm joined by Julie Van Kampen. She is the Deputy Commissioning Engineer for the James Webb Space Telescope. We had a wonderfully active and successful morning where the second wing of the primary mirror was deployed, and we are now in the final phases of latching that mirror in place. Julie, can you give us a little bit of an update as to what's going on right now and some of the commands that we're hearing from the model?
Look good. You're go to continue with the motor move.
This is they're getting ready to send.
Yep.
They're getting ready to send the very last move command to latch the bottom latch of the mirrors that were deployed today, the wing that was deployed today with the 3 mirrors on it. This last command will take a few minutes, and it will pull the latch into its final full load. And we will hear them talk, and as they give that last command, and then finally they'll verify that the command was successful and the motors brought it to full load. And you can see everybody here in the room is ready to see that last and final stage. This is the very last move of our deployment sequence for the structural deployments for JWST.
Just incredible. It's been an amazing little bit more than a week now. It launched on December 25th, and then the amazing sun shield was deployed. The scope began to cool, going down to an operating temperature of close to minus 400 degrees Fahrenheit. And after that, we had the deployment of the secondary focusing mirror. Then yesterday saw the deployment of the first wing of the primary mirror. And then today the second one, and now we are finishing up latching that into its final stable configuration. Those latches will not be touched again. The mirror will be in its final configuration, but that's not the end. In the weeks to come, there are some pretty important things coming up, and maybe Julie, as we're waiting for this final conference, give us a sense about what's coming up next for the commissioning of Webb.
Yeah, over the next several weeks, as you had talked with Lee Feinberg earlier today, we'll be taking the mirrors off of their launch position, and they're up against hard stops. We'll be moving them a half an inch forward. Once they're all a half an inch forward, then we'll start the steps involved in actually turning our mirror into a nice clean image. One smooth mirror. We'll first figure out which mirror is which for the images that we see off of the sky, and then we'll bring all those into one image, and then we'll start to actually change the mirror to make sure it's all in one shape. We'll also move the secondary mirror, which is a couple of days ago we deployed the secondary structure. You can see people starting to get nervous here in the room.
Love that. That's right.
Yeah, they can just kind of see the tension there. We'll bring the secondary mirror off of its hard stops too, and move that forward and back and do a final focus adjust of the telescope. During that time, all of our instruments are cooling down and being powered on and checked out for the first time. We'll move our filter wheels and all of our mechanisms inside the instruments. We'll check out our detectors and make sure they're operating and they're at their proper temperatures. And then the motor move is halfway. And the final thing that we'll do is we'll start taking images and calibrate those instruments. We'll make sure that everything is set to go and ready to start our early science operations, which you heard several of your scientists talk about today.
Absolutely. There's a question that we get a lot on social media. It might be kind of fun to take the time. And like I said, we will break our commentary when we see that the command has come through for that final latch. But Kelly on Facebook asks, how do infrared signals taken by the James Webb Space Telescope get translated into pictures? Are the pictures we will get the same as if we looked at it up close with the
All
naked
stations,
eye?
at this time we have a nominal LOS on DSS 36, our backup antenna at Canberra. We will continue to have telemetry on the prime antenna for another 10 minutes. Command coverage will end in 4 minutes.
As the Earth rotates, there are different antennas that the James Webb Space Telescope is using to download its telemetry to tell us.
CC,
so that was just an announcement
GSE
about
on
that.
Opt. At this time, LA command button. I see that on the ground, Cecil. That keyword looks good. CC, you are correct.
Executing.
All of us are listening for that command. That confirmation that the mirror has been latched
This is
into
step
place.
lead on ops. We've only had 5,000 steps remaining in our final latch preload move. We're down to 4,000.
Copy.
3,000.
You can see the excitement.
1,000. And we have a fully deployed JWST observatory.
All right.
Yes. Thousands of people around the world have worked on this observatory. You see here the people at the Space Telescope Science Institute in Baltimore, Maryland. Having a moment of celebration. Hopefully we'll get a little bit of audio from that room too. Even if we don't, we can see the joy on their faces. Everybody, of course, being very, very careful with the COVID surge. I'm joining you from an isolated room so I can talk to you without a mask on. Everybody else is wearing their masks. But what a wonderful day. Even though I'm a floor below the control room, I can hear people cheering in the background.
All stations, this is Mom on Ops. As you heard, definitely we have a telescope. Stand by for the project manager. Stand by.
Copy.
Okay. Yeah, I just want to thank everyone and congratulate them on today's mirror move. The last 2 weeks have been totally amazing. Thousands of people have worked on JVST at this point to get us here. But I have a couple of special shout outs. One to the deployment team, You guys have done a phenomenal job over the last 2 weeks, but also over the last probably 15, 20 years to get us to this point. I do want to also thank the Northrop INT team and the Goddard folks who participated in the actual stowing of the observatory about a year ago. If they hadn't done it perfectly, these last 2 weeks would not have gone as well as they have. Finally, on a personal note, I will tell you guys every single day I am honored and humbled to be associated with this team. And I want to thank you all. Go JWST.
All stations be advised in just a few seconds, Station 3-4 will bring down the uplink. We will see a brief loss of telemetry at that time while they reacquire the downlink.
Copy that.
You can hear me also. I'm Thomas Zerbook, and I'm the head of science at NASA, and I want to tell you just how excited and emotional I am right now. We have a deployed telescope on orbit, a magnificent telescope the likes of which the world has never seen. So how does it feel to make history, everybody? You just said it. We're coming on the other side of a time that most of you would have spent with your families, and with a time that, frankly, even the last year, where most of you worked way harder than perhaps you ever worked in your life. And I just want to tell you how much I personally, and we as an entire team, appreciate your sacrifice that you've given, and also your family, your families, the sacrifice they've given to this amazing history-making telescope. To me, you know what? Words cannot pay you back. Just know how deeply we appreciate and how deeply we value everything you've done. Bill, it has been fun to watch you and Scott working together with Greg and all the other leaders, kind of really building an amazing team. I think of it as a championship team. You never know how great the team is until you see them out there on the field. I love what I see. We all love what we see. It's truly an excellent team, and you've shown the whole world. You cannot believe how many letters and emails I've gotten from around the world kind of congratulating our entire agency, our entire country, our entire team, the international team for this work. Of course, NASA Goddard is leading with so many of the team members here. Thanks to each and every one of you. Northrop Grumman, it has been fun to get to know you and be with you on this journey. I'm only for 5 years on this journey. Many of you have been here for 20 or more years, and some of you are not even right now here anymore, or because there are other projects, or some have retired or no longer with us. We think of them also in each one of them. Space Telescope Science Institute, what a great place to be here, looking out at the trees as we think of the deep space, and being a single team here. And then, of course, the partner that's going to add a lot here going forward and
role is Ball Aerospace, as we're starting to work with this entire team going forward. So what I'd like to do is quickly just introduce somebody else. And frankly, I have him here on the phone.
He's the head of science at NASA.
I want to just tell you, the person that I have on the
audio
phone
trouble
is a
there,
person
but as you can see, he's expressing his thanks and his emotion at this amazing accomplishment of deploying the James Webb Space Telescope.
I actually have not received more texts from anybody else except my kids in the last few months and weeks than my friend
see if
Blake.
in a few more minutes we get any more audio.
How much I appreciate his work and his partnership and friendship as we go forward. So I wanted to just see whether he wants to add a couple sentences. You tell me whether it's going to work. Yeah, hang on for one sec, Blake.
I think we lost Thomas's audio, but he was just talking about how much of an honor it is to be part of this incredible mission. And I think they may be working on his audio right now. It's something that you hear a lot from people at NASA about how privileged we are to work in this group. It's something that you hear a lot of people say, but I have to really reiterate just how much we feel this. It is a tremendous honor and privilege to work on something large and to have a goal that, I believe, is noble. We are trying to advance knowledge. There are risks. We have never deployed an observatory like this before. Tens of thousands of people are actually waiting around the world for this to work, who have worked on this, who have given years of their life, as Thomas just said, their family as well. So I think with that, we're going to leave Thomas to give his conclusions. I hear some applause in the background. Okay, so the final guest we have is head of NASA, the administrator of NASA, Bill Nelson. Bill comes from a huge amount of experience, a former senator, and I might also mention a former astronaut. So, Bill, it is an honor to have you here. Please give us your thoughts on this historic moment. And unfortunately, I think you may have to unmute, Bill. That's always the case, isn't it?
I am unmuted.
There you go.
Okay. I want to say again what Thomas just said and what Bill Oakes just said. It's an incredible team. NASA is a place where the impossible becomes possible. And that's why so many people have stayed with NASA over the years. That's why 9 years in a row, NASA has been voted as the best place to work in the entire federal government. 9 years in a row. We bring in and we value our interns from college, and we bring them in, and 30% of them end up having a career at NASA. And then we have these incredible partners outside of NASA that Thomas has mentioned. Just take the aerospace company, Northrop Grumman, that oversaw all this. Take the people at Goddard, take the people at the Space Telescope Institute. This is just incredible input. Think about the delivery and packaging of that telescope when it was put on the ship. And they had to have special security going through the Panama Canal. And then, of course, Arianespace. I mean, right on the money. And our international partners, which are so important to us. In this particular mission, the Canadian Space Agency, the European Space Agency. But in NASA at large, we've got over 30 to 50 partners, for example, internationally involved in the International Space Station. And look at the politics on Earth where it's so rough between Russia and the United States, right to today, over terrestrial matters. And yet, what's happening up in space? We're cooperating, and we've been cooperating in the civilian space program ever since 1975, when an American spacecraft and a Soviet spacecraft rendezvoused and docked, and the crews lived together for 9 days. And that has continued all the way up to today, where they, the Russians, have helped us build and operate the International Space Station. So I give you the examples because when people put their mind to it and start cooperating and working together as a team, as we say at NASA, the impossible becomes possible. And here is another example of that. So how can I thank you enough? How can I thank the support that we've gotten from the White House? President Biden specifically is watching this mission. The Vice President, Kamala Harris, same thing. Our partners in the House and the Senate, my old colleagues that I love to continue to harass, and yet they have supported this. I want to single out one person because James Webb is long overdue and it's way over budget on the original budget. But James Webb was kept alive in large part by Senator Barbara Mikulski of Maryland, now retired. I've called her personally to thank her. And indeed, this is a proud day for her too, because when it was needed for additional appropriations, she was there. So what a great day. Now we got a long way to go. We got to get out there to day 29, and those thrusters have got to work to get us into that orbit around L2. A lot of other mechanisms to work, and then it's going to take us about 6 months to start receiving those pictures. But when we do, as you have had Michelle explain to you, the horizon is not the limit. We're going to have all kind of new knowledge about who we are, what we are, where we came from. Are there others out there? Is it any wonder why it's such a privilege to be involved in NASA? So, just like Thomas, I'm emotional too. Thank you. Thank you.
Oh, thank you so much, Nelson. It's an honor to have you here with us. And yes, it's a very emotional day for all of us. Absolutely incredible. So on behalf of everybody here at the Space Telescope Science Institute, this will actually begin the conclusion of our broadcast. It has been an amazing couple of weeks, actually. First, the run-up to the launch, then the launch, the successful deployment of the observatory. And we look forward now to a few more months until we release those first images, and they will prove to be amazing. We're all just so happy to be here. Again, what we were saying before, that it's easy, you keep hearing it again, this team of people. As much as I love science, I've been fascinated all my life. The best part about working at NASA are the people around us. None of this is possible without everybody listening here today, people that are members of countries all over the world, people who can support science through their tax money, people at universities, seriously everywhere in every country that there is. We are all in this together, and this is something amazing that we have just begun, this new journey to have an entirely new view of the universe. It's been an honor to be with you through this part of commissioning. I hope to be later on as this continues. So this is Michelle Thaller wishing you a very good day from the Space Telescope Science Institute. So much for joining us.